So let's get started. So how many people already know about machine learning? So you've done linear regression, logistic regression, decision trees. So only a few. So last time we're looking at logistic regression. And so your assignment will, I'm looking at some data to do both logistic regression on it, to classify it, and to do decision trees. And once you figure out the assignment and how to actually do it, it shouldn't be that difficult. I was going to have you also do it on AWS, but I think it gets too close to exam, so I'll postpone that until after the exam. Yeah, so basically when we're doing the logistic regression, we're just basically trying to, instead of map it to a straight line, to this function, right? Now, so looking at examples, we're just doing it directly. And Spark has what they call a pipeline, which allows us to create the various steps. So there are times when you need to transform the data somehow, and then you want to apply linear regression or decision trees. And then we put that all in the pipeline and then execute it all at once, which also allows us to save the pipeline so we can use it other places. And also, we have these hyperparameters for all these algorithms. And the question is, which hyperparameter do you want to use? And we'll see later that we can use a pipeline to specify, try these n hyperparameters. It will then try them all on some subset of the training data to figure out which hyperparameters will give us the best model. So we don't have to manually, run it over and over again and check it out. So it's pretty simple to deal with it. It's just we need to create various components of the pipeline. And so in this case, I'm creating an R formula and a logistic regression. And here I'm adding it to an array, and I can just add that array to the pipeline. And then when I want to actually train the model and use it, I read the data, I split it into my training set and test set as normal, and then I can use a pipeline to fit the data and get back a pipeline model, and then we can get the actual linguistic model, logistic model out of it, and then continue from there. Right, so it's a way of taking all the steps you want to deal with, transform the data, maybe you need to scale it, do various things, fit it to the logistic function, and then apply it, right? So nothing earth-shattering. And then here I'm getting a test data. The problem is now the model expects the various columns we set up properly. So I use our formula here, and now I can transform it and get the result, right? And so if we get basically the same thing we did directly. Nothing earth-shattering, so we can now put things in pipeline. Second example. So this is some data. I'm not sure how realistic it is, whether it's actual data or they just made it up. You basically have whether you admit people for the graduate school based upon GRE, GPA, and the rank of the school, right? And so we want to then train, right, a model so that we can then, presumably next year, we can just say, here's the data, tell us who to admit, right? And so again, it's pretty straightforward. You have to read the data. Again, I'm just using, right, the schemas, make sure I get the right type. And there's like 250 data points. And then I create a pipeline, and the pipeline, well, what formula do I want to use, right? In this case, I want to admit to be dependent upon GRE, GPA, and rank. And I'll use logistic regression, and then we can fit it and get the model out, and then get the various coefficients. And you'll see that one coefficient is negative. Well, that makes sense because 1 means it's a higher ranked school and 4 means a lower ranked school. So you'd expect them to admit more students from higher ranked school. And so that relationship is inverse, right? And so the weights, the GRE score has the lowest weight, right? So that's not weighted very heavily. And then the GPA is weighted more, most, and the rank is ranked to use a lot more than the actual GRE score. And then we can do the same thing. We can take our test set and apply it, and see how the model predicts it, right? And this interesting thing is, where does the model differ from what the actual data did, right? And so here is just, we now know how to start manipulating the data. So I can say, give me all the rows where the label, right, that is whether they emit or not, is different than their prediction. And then we can start looking at it. And of course, some things don't make, for example, well, here we have a student 4.0, top ranked school. The GRE score is not that great, but the GRE score, the model doesn't weight very heavily. So the model said, admit them, right? Because it's like, okay, they have a the highest GPA you can get and give them the highest ranked school, but they deny them. And we can then, we can actually find, here's someone, GRE score, maximum, GPA, I mean, it's close to maximum, and school is best, right? And they did not admit, but of course the model says admit. And then you get something like this, where you have someone who's got a GRE score of 300. I mean, 300, and their GPA is 2.84, and they come from a second ranked school, not a first ranked school. It's like, really? Why did you deny this person and accept that person, right? In all measures, the second person is significantly worse off, right? I mean, a GRE score of 300? I mean, what's that? Yeah, I mean, yeah, so there's all these other parameters that we don't have data for, right? It could be, you know, they're somehow related to school, right? They're, like you said, the right, you know, the dean's son or something, or who knows, right? You know, or the father just donated $100 million to the campus, and so like, oh, I mean, letter of recommendation and all kinds of other activities. Who knows, right? The other thing that can happen, it could be that that person applied very late, right? And by the time they applied, they'd already used up all their slots. And it's like, yeah, you're a good student, but except you're sort of, you waited too long. But, so there's a number of things we don't know. But again, it's like, how does our model, where does it differ, right? And the other thing we can do is then look at the different types of errors, right? There's false positives and false negatives. So one thing that's common is they create what they call the confusion matrix. And I have no idea why it's called the confusion matrix. And that is your computer matrix of, you know, when the model matched what happened and when it was different, right? So you have 4 entries. We get here. I'm just showing you where it differed, right? Where the confusion matrix will have 4 different entries. One is you agree with the model when accepting, you agree with the model when you deny, and when you disagree with the model on acceptance and disagree with the model on deny, right? Here I'm just looking at where it differed from the model, right? So there are 10 places where the model said deny, and they actually admitted them, and 31 cases where you know, they actually admitted, and the model said don't. And presumably that person with a 300 GRE score and a 2 point, right, was one of them. But it gives you some insight into how well the model performs with reality. And the question then is, if you start changing hyperparameters, how do we measure the goodness of the model? We'll see this in a minute. And again, here's where the model went wrong, right? Part of it is, you know, their acceptance policy clearly was not captured by those 3 parameters. So how can we then tune the hyperparameters? So there's a couple of things we need to do. We can create a pipeline which will then do it for us, but we need a way of specifying here's the parameters we want to vary and what they're going to be. We do that with a parameter grid builder. And then we need some way of evaluating the results. And then we have to again, split the data into more pieces, right? Because we don't want to use the same data to basically train the hyperparameters as we use to train the data. Because then you'll overfit the thing. So again, we read the data. I can create the pipeline the same way, right? I'm basically saying I want to use our formula, logistic regression, but I'm not specifying any parameters here. I could, but what we'll do is in the grid builder, we can specify the parameters we want to use. So I'm specifying for the R formula, one just use a GRE score. The other one is GRE score, GPA, and the rank. And then for the elastic net parameter, say use 0, 0.5, and 1. And now when we run it, it's going to then, create models using all combinations of these parameters, and then try and fix the best model that it came up with. Create a binary classifier. There's basically only two options: area under ROC, another one. And then our train validation split to basically split the data in two pieces. Use 75% for the training, and another 25% to train hyperparameters. And you have to tell it how to estimate the parameters, the pipeline, the evaluator, and then we just say fit, right? And that then it takes longer because it's going to go and it's going to take all those combinations of hyperparameters, create a model for each one, and then use this fit model to figure out which one to use. Again, hardly exciting, right? But it allows you to not have to run the model multiple times to figure out which hyperparameter might be better for this. In this case, right, when I look at the errors, the outcome is completely different, right? There were more errors, right? The model was different from what actually happened more times than before, but they were all false positives or no false negatives. And the question then becomes, is that a better model or not, right? It depends upon what's more important, right? There are times when you may want more favorite false negatives over false positives. This is where the sort of art of machine learning comes in, right? Because you're tweaking the parameters to figure out which model might be better, but it's only better perhaps on this data set, so you have to figure out what to do. And I ran this experiment several times in several hyperparameters and trying to change them. And the output always seemed to be the same when I was trying to train hyperparameters, and I couldn't figure out why. And it could be that, it's a small data set. The other problem is that, as we saw, there are some people who had good school, high GPAs, high GRE scores who were not admitted. Some people with low scores and they were admitted. So it's, I didn't have the time to figure out, okay, why is it when I selected one set of hyperparameters and ran it, I got one result. When I tried it in multiple ones, I always got the same result. Don't know. The question is, I basically create a model multiple times, right? And the question is, did I use the same split each time? And yes, I fixed the split, right? And then I ran the two set of models, yeah. Otherwise, yeah, and that's another part of, why this is um, part of an art, right? Because you have to, when if you got particularly if you got a small data set, right? You pick your training sets, um, you do it again, you get different subsets, and it's going to train differently. And that's one reason why there's a whole course of machine learning, right? That you have to learn all those subtleties and how to deal with it. Um, Otherwise, you just crank through. Um, who knows what will happen, right? Um, so now I want to look at some transformations and then sort of motivate decision trees. Um, so Spark comes with a lot of different transformations and way to extract features. A number of them which are designed to extract words from text and then to ignore certain words, usually that the word like a and the and, really not important. So you want some ways of getting the words, extracting the unimportant words, and focusing on the real words. Um, so there's a bunch of them for scaling data, and this becomes important, particularly when you're doing clustering. You measure how far things are apart, and if you scale one dimension differently, that can affect how far apart points are. So it becomes important to have a uniform scaling. And so there is a standard scaler. Um, and so what it does is that each feature is going to have standard deviation 1, and then you can set what the mean to be 0 or not. And by feature, they mean column here. So here's the input data, the features, and the scaled features, right? So the first column, 1, 2, 3, well, the standard deviation of that is 1 because you got 3 points and there's 1 exactly in the middle of the other two, right? And they're 1 unit apart. Here they're farther apart, and so yeah, so it scales it. And the same thing with -1, right? There's a min-max scalar, and so you can specify a range, right? So I want all the data between 0 and 1, or 0 and 10, or and again, you do it by column, and so to map 1 through 3 into 1, I mean, 1 goes to 0, 3 goes to 1, and then 2 is in the middle, so it goes to 0.5. Right, and that, again, there are some subtle points you have to worry about when you're scaling data. This scale just keeps relationship between the elements, right? Whereas when we start doing by the standard deviation, things will get closer farther. I mean, they don't, the ratio before and after, how far apart they are, can change, right? And it's pretty simple to use them. You just, here's some data to deal with it. In this case, a min-max scalar, input columns, output columns, and again, there's two steps. One is fitting the scalar, so it knows, oh, okay, here's the max, here's the min, and then you can use the transform to actually rescale the data. Right? Absolute, max absolute scalar. Again, we're just looking at the we're scaling it to a slightly different range. Actually taking continuous data and transforming it to categorical by converting it to buckets, right? Some algorithms work better with categorical data, and some algorithms require continuous data, so being able to go from one to the other. Also, if you've got very sparse data, using continuous may be better to group them into buckets. And so it does that, right? And you just basically tell it what the range you want the buckets to be. And you don't want any data to be outside the range. That's where they go from -infinity to -5. That creates one bucket. From -5 to 0 creates another bucket. 0 to 0.5 is another bucket. And so it just transforms the data into those. In this case, there's going to be 1, 2, 3, there's 4 buckets. And they're labeled 0 through 3. Related is, instead of creating multiple buckets, there's only 2 buckets, basically A or B, 0 or 1. And then you can you basically set, where do you want to divide. And then it'll put things in those buckets. again, this the quantize greater, again, if we're going to take a continuous and map it to category features. So example here is we have a column that represents time in hours, and we can now map it in the case how many buckets I want, and it's going to divide that range into 3 separate buckets. The string indexer, it takes a bunch of strings and it maps them to numbers, right? Which becomes useful because, for example, if you want to do logistic classification, your features have to be numerical, right? We cannot use string inputs as a feature for logistic regression. And so this is one way we can convert discrete into but there isn't a slight little gotcha here. What happens if your training set doesn't have a string which your test set does, right? So what happens when you don't have all the possible strings in your test set? And you can specify what can happen. One is throw an exception so you know something went wrong. You can tell it to skip any rows that contain that unknown string. Or you can tell it to put them into a special bucket. So the question is, can it basically retrain itself? Well, now you have a problem, right? The problem is to retrain yourself, you have to have data which contains that string.
Or are we just assuming if there's one string, there's nothing?
Right. You don't know what it is, right? Yeah, so the one option is just skip it, right? Right. But you have to, well, again, but then you're going to have to go into your data set and find what string it was, right? And then figure out how to modify your training set, but you don't want to do too much changing to that training set, right? Because
yeah, I guess the better way to throw it in one bucket after you've gone, then go back and all of this, all of it. I'm just kind of, yeah, I'm kind of thinking about this as this like the hard IT category.
right,
How this works. The real world, you're actually set many more columns. So
right.
draw the correlation columns 6 through 10. So again, learn.
Yeah, they don't. That level of intelligence doesn't belong in the string indexer, right? So that would be something that you're going to build on top of their tools. And you have to be careful because again, you have to find what's missing, and then how do you associate it? Do you want to bring that information from the training set and the test set, the training set, and that gets careful because you're right, right,
And there are algorithms.
right. And there are a million things that go wrong, right? And people have been working this a long time, and they keep on finding, and solutions to all problems, right? Um, yeah, the one hot encoder. I have no idea where the name comes from. Um, and the importance here is, we can take a category with strings, we can map them to basically buckets, right? Using what we saw before, but that's still not good enough for logistic regression. We need to convert it to continuous features, and that's what it'll do for us. So it's a common practice to logistic regression when you've got a categorical feature is right. You first convert it from like strings into numbers, and then use a one-hot encoder to get it in the format so the logistic regression can use it. There are a number of problems that comes with this. Even going from these categories to these indexes, where somehow we're saying that B is twice C, right? We're putting we're taking strings which may have, or there could be 5 different types of strings, right? But we're actually mapping them into numbers 0 through 5, right? And so somehow that fifth one is farther away from the first one. We're imposing some linear structure on it, which may not make sense, right? And so that's one problem with taking categorical features and mapping them into numerical numbers so we can then use them in something like logistic regression. So far, so good. Then there is the SQL Transformer, which basically allows you to use a select statement to take columns and transform them into something else. The syntax is a little weird. You need that from this. But literally, we can create a data frame like this, and then we can do a select statement now to add more columns based upon, right, that, so this will take this data set, and we're selecting everything, and we're adding a V3 and a V4, so V3 is just the first two columns combined. So it makes it easy to do transformations. And this slide will come later, but it does show you, I just say that the logistic regression, it can handle up to 10 million features. I'm not sure why they want to go so high, because if you've got 10 million features, that's a huge space. And so unless you've got tremendous data set, it's going to be very, very sparse. Decision trees, thousands of features. So the last thing I want to talk about is decision trees today. I don't know about you, but when I was growing up, we played this game. Some people call it 20 questions. You'd think of something, and then people were supposed to try and guess what it was by asking you questions. Like, is it red? Is it green? Is it, in the room? And you can answer yes or no, right? And the whole point is, you can ask, in the formal game, you can ask up to 20 questions, right? And if you can ask the right question to figure out what it is, but before you ask 20 questions, you win. And if you can't, then the person who thought that thing loses, right? That is decision trees. End of story, right? So the example here, so in the Titanic data, right, there's a number of features. Of course, perhaps, does everyone know the Titanic? Is that?
I don't know the Titanic.
You don't know the Titanic story? Well, basically, the Titanic was this huge passenger ship, and it was thought to be unsinkable, right? It had double hulls. It was supposed to be the unsinkable ship. And that's where that quote comes from, right? And so it was like this unsinkable ship. And so sure enough, what happens on the first voyage, right? It sinks. Why? Well, because we don't have to worry, because this ship is unsinkable. So you're going near icebergs. Who cares, right? Oh, we got too close. Oh, too bad, right? And so the assignment is, to model who survives, right? Is it better to be a male or female, a first class, second class, third class? What features are there that leads to a higher survival rate, right? Or the captain, right? So to play the 20 questions game, we've got certain features, right? The sex, the age, the class, the cabin class they were in, how many family members were on the crew, and so we could just start saying, okay, are they male, right? And if the answer is no, then we can start asking, how many survived, right? If they are male, then we can say, okay, they're older or less than, right, this age, and then we can keep on going on all the features, and finally we get down to we've asked questions about all the features, and then the leaf nodes. If we're good, we get either 100% or 0%, right? We then have and then we build this model up, and then when you go to actually use a model, you just take that data and you just follow a tree, right? Boom, 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 and then okay, we got down here, so basically we'll 2% died, so we'll assume that they survived, right? This is decision trees. So it's a very simple model, right? It's very easy to explain. But now the problem is, when you play the game, right, the goal is to figure out the answer before we get to 20 questions, right? And there are times, if you ask the wrong questions, you just keep on going and you don't get enough information and you lose. And so then the process becomes, which questions do we ask when, right? And so we want to basically minimize the depth of the tree, right, to get down to the leaves. And so the question becomes, how do we decide which question to ask first, right? If you've got n features, which one do you want to start at, saying, should we do age first, or should we do sex first? And so we need it's going to be an algorithm, right? So the algorithm has some way of determining, okay, I'm going to start here. And this gets us into information theory, which some of you have probably seen before if you studied what comes up almost everywhere. And so we want to quantify information, right? And so if we've got some event, we'll say that the information of that event is minus log 2 of the probability of that event occurring. All right, so that this comes from the work of Shannon in the 40s. Worked at Bell Labs to figure out how much information is in text when you send it across the wire, how far can you compress it, etc. So that definition of information, if the probability of an event occurring is 0, then the information is 0. I mean, if it can't occur, to know that it doesn't occur doesn't tell us anything. It can occur. The same thing, the probability is 1, right? Then it's always going to occur. So knowing that it occurs doesn't tell us anything because it's always going to happen. There's no information there, right? But as the probability goes from 0 to higher, that the amount of information we get increases, right? And it increases up to 0.5. And then of course, it decreases down again. Okay? So we have a sort of mathematical definition of information. So we can look at this in this example. We have a deck of cards, right? There's 52 cards, and Again, we're going to play the 22 questions, and someone's going to select a card, and you can say, guess which one it is, right? And so then we can ask, here's two possible questions we can ask, right? Is it a red card or not? Another question is it a picture card, right? Meaning the jack, queen, or king. And then we can ask, well, what question would be better to ask, right, first? And so we can then start asking, the probability of it being red is 1/2, right? Because there's half of the cards are red, half of the cards are black. And then we can say, the information content when the answer is yes, right, is right, it's minus log of 2 of 1/2, which is 1. The probability of it being a picture, again, there's 12 cards out of 52, which are picture cards. So that's 3 over 13. Information content is 2.12, so it's higher, right? Then we can ask what happens if Wolf is black. We get the same situation, right? But again, it's probability 1/2, so it's 1. But not picture, there's a lot more which are not picture, and so the logarithm becomes smaller. So we get, if we ask the question, is it red or not, we get the same amount of information because, right, either half the time it's yes and half the time it's no. If we ask if it's picture, right, sometimes we get more information. We actually shrink down the possibilities much farther, right, depending upon the answer. But that doesn't tell us which one to pick, right? So then we come across this idea of entropy, which presumably you've seen in your career someplace before. We can think of entropy as a measure of uncertainty or disorder. But if it's a measure of disorder, it's also a measure of order, right? Going one way if it's disorder, then going the other way is order. And so the information area, we can find entropy as with some of all possible events, right? The probability of it occurring times the information of that event. And that will then give us some entropy of that situation. And the smaller the number, the more orderly it is. So now we can ask, well, if we ask a question red or not, what's the entropy of asking that question? Well, it's the probability of it being red times information content of being red plus probability of being not red times information content. But the probability is 1/2 for each, and information content is 1. And so entropy of that asking that question is 1. The picture not picture, right, we can now do the calculation, the probability of it being a picture, plus the probability of it not being a picture times the information content, and we get a lower entropy level. So far, so good. Now, how does this help us decide which question to ask first? Well, our goal is to have complete order, right? To know exactly what's going on. That means having entropy being 0. And so as we create our decision tree, right, we can compute the entropy of before we ask any questions, after we ask the first question, after we ask the second question, right? And each time we want the entropy to get lower and lower and lower. Until we get to the bottom, hopefully the entropy is 0, because then it says, okay, we know exactly what's happening, right? I know the answer, and the card you picked is a Queen of Hearts, right? And so what we want to do is we want to ask a question which produces the lowest entropy. And so there are a number of different algorithms used to create decision trees, and most of them use entropy to decide which question to ask first. Yeah, it's counterintuitive, right? Because you're thinking about the one path you're going to take. But you're also creating a deeper tree, right? Right. Yeah. So basically, we really want to ask the question. We want to pick the question in which, well, what they call it's called information gain, right? Which is how much entropy decreases, right? The more it decreases, the more we've learned, because we've gone from a more chaotic system to a less chaotic system, which means there's more order, right, or more information. And so the goal is to, well, it's a greedy algorithm, right? How can each step we want to gain as much as possible. Now, greedy algorithms don't always produce the best algorithm, right? And they don't always lead you to the best solution, right? There's all this problem of local minimum, local maximum, right? And so if you get stuck someplace, a greedy algorithm is going to bring you to local maximum, local min, but there may be a higher min over here. How to get there? Well, the greedy algorithm is not going to go down again and go back up again, right? So what decision trees do is typically you have a number of features, right? 1 through n, and then we can since it's a computer and it's an algorithm, it's going to like, okay, what's the change in entropy when I ask split on the first feature? What's the entropy change when I do it on the second feature? And I'll go through all n features and I'll pick the one that has the greatest decrease in entropy.
try like combinations, actually find the lowest entropy.
No, so
it's just step by step.
It's step by step. So you start with the first node and you say, okay, I've got n features. Which one should I add? What one should I spit on first? You then measure the entropy in all n, and you pick the one that has the lowest change, highest change in entropy. And that's the first one you ask. Then that gives you two subtrees, right? And now those two subtrees, you ask the same question independently in the two subtrees. On this subtree, right, what feature should I split on next? You don't go back and second guess. And the answer on the two subtrees may be different, right? And so this is all transparent, right? But when you do a decision tree, you basically say, I want to use a decision tree, and I want to use this algorithm, and here's my data, and then it does this. All right?
Yeah. Specific set. If it's like that.
If you want to improve on it, yes, what you do is you don't use one tree. You use a forest of trees. And that's very common, right? So in Spark, you could create a single decision tree. Or there are two algorithms you use to create a forest of trees, and then each tree is be different. And then when you
I get it.
well, nothing we've talked about in terms of logic regression or decision trees. These are all common implementations, right? Whether you're doing in Python or Julia or any of the other libraries do machine learning, MATLAB, they're going to have the same algorithm implemented, right? The one what we gain in doing in Spark is if you've got thousands of features, right, and you want to do forest of trees, and you've got 50 machines, right, you can do it faster. I don't know how Spark will treat some forest of trees, decision trees on the machines. I don't know because each machine a different tree, presumably, but I just don't know. And when decision trees have, in Spark have a bunch of hyperparameters, and the first one is which metric you want to use for information gain. And entropy is a common one. There's also another one called Gini, which there's a mathematical explanation of it. It's another way of trying to measure which feature to use first. Another feature is the maximum number of bins. The problem we have with decision trees is what happens when you get a continuous feature, right? What you do is you take that continuous feature and you break it into bins, right? And you can say, okay, say I'll break it into 2 bins, age, right? Everyone less than 50, everyone over 50. But then you can then repeat the same process on the On the split that says age under 50, you can now ask the same question on age again, because now you can break that in more bins, right? Until you get down fine enough where it's close enough. How deep do you want that tree to go? Particularly if you have lots of continuous features, right? You've got 50 continuous features. You could conceivably each feature could give you 10, 20 levels of the tree. In the min info gain, again, if you have continuous features, you could keep on asking over and over again and just get smaller and smaller gains. At some point, it's like, well, when you're not making any progress. Right, and so decision trees have some benefits. One is they handle categorical features very well, right? If they're sort of designed for categorical features, you basically don't have to break up continuous features into categorical and like dividend. Whereas logistic regression will do the opposite, right? We have to take categorical features and map them onto some sort of continuous feature. It's also, it's pretty easy to understand how it works, right? I mean, you just 20 questions. Linear regression is pretty easy too, right? Because it's like, okay, it's just a line. And then logistic regression, okay, well, it's got this crazy, logistic function, and somehow we're mapping it into there. What does that really mean? We could sort of think it, sort of similar, but this is pretty simple. You also don't have to worry about scaling things because the question is, are we restricted to binary trees? No. If the max number of bins. So when we have a continuous feature, right? Or if you have, say color, and there's 5 colors, you could then separate it into, we don't have to do red or not red. But again, all that is handled by the algorithm, right? And that does lead to one of the problems with machine learning. You have your data, you have your training data, you train it. And why does the algorithm then, when you use it, why does it say do this instead of that? Right? You don't know this. Well, because I was trained on this data set, and questions? So I did update the reading list. There's a chapter in the book that talks about Spark ML. Also, the Spark documentation has a section on MLlib, and it divides it into the RDD part and the DataFrame part. though there are various points in the data frame section where this says, well, go read the RDD part, it's the same, except for these minor changes. So if you look at that documentation, it shows you how to do these transformations. It shows you how to use various, how to create a decision tree, how to create a forest of decision trees. Okay. Yes, November 2nd. Just a reading. What's that? Yeah, at this point, I have no idea what will be on the exam. Yes, and the readings, yes. What's that? Not yet. If no other questions, I think we're done for the day.